Hi everyone, my name is Seongjun from Korea University. I'm here to present our paper, Neo-GNNs, Neighborhood Overlap-Aware Graph Neural Networks for Link Prediction. This is joint work with Seoyoon Kim, Junhyun Lee, Jaewoo Kang, and Hyunwoo Kim. We first explain neighborhood overlap-based heuristic method for link prediction, which was the motivation for our work. Given node pairs, neighborhood overlap-based heuristic method measures scores of given node pairs based on structural information of overlapped neighbors. The most typical neighborhood overlap-based heuristic method is common neighbors. The common neighbors method measures the score of the given node pair by counting the number of common neighbors between two nodes. This method is simple and effective, but has a limitation that equally weighs the importance of each common neighbor. To solve this issue, several heuristic methods measure the score for the link by considering the importance of each common neighbor. From the intuition that neighbor nodes with lower degrees are more significant, they give more weight to neighbors with lower degree. Resource allocation measures the score of the node pair by counting the inverse degrees of common neighbors between two nodes. Atomic ADAR has a relatively decreased penalty for higher degree compared to resource allocation by using the reciprocal logarithm of common neighbors' degrees between the two nodes. These neighborhood overlap-based heuristic methods are straightforward yet highly effective for link prediction. Now, here is the question. Can conventional GNNs generalize and outperform this neighborhood overlap-based heuristic method? The answer is no. As can be seen from the table, conventional GNNs often show poor performance with a huge gap than that of neighborhood overlap-based heuristic methods, which implies that GNNs cannot generalize these heuristic methods. This is because structural information such as overlap neighborhoods, degrees, and shortest paths is crucial for link prediction, whereas GNNs heavily rely on smooth node features rather than structural information. Also, conventional GNNs have not been designed to estimate overlap neighbors. To address these limitations of GNNs, we propose neighborhood overlap-aware graph neural networks that learn useful structural features from an adjacency matrix and estimate overlap neighborhoods for link prediction. We first explain how GNNs can be designated to estimate overlap neighbors and learn neighborhood overlap-based heuristic methods. First, as we discussed, each heuristic method uses manually designed structural features of neighborhoods. To generalize and learn these structural features, we propose structural feature generator fzeta, which learns to generate structural features of each node using an only adjacency matrix A of the graph. fzeta is a learnable function comprised of two MLPs, fzeta node and fzeta edge, for nodes and edges respectively. Now, structural feature generator can generate structural features for each heuristic method. For example, if fzeta node is a reciprocal of the logarithm function and fzeta edge is an identity function, then structural feature generator fzeta can generate the exactly same structural feature as the features used in atomic ADAR method. Now, each node has a generated structural feature. Then, the next process is to construct diagonal matrix using the structural feature vector. This makes GNNs maintain the respective features of each node after aggregation, which can detect the neighborhood overlap. Then we aggregate features of neighborhoods via a multi-op way to consider multi-op overlap neighbors. Note that since the normalized adjacency matrix hinders GNNs counting a number of neighborhoods, unlike conventional GNNs, we use an unnormalized adjacency matrix to consider the number of overlap neighbors. After the aggregation step, now each row vector of Z involves all the features of each node's neighbors individually. Then, if we compute the inner product of two row vectors in Z, then we can compute the similarity score of the given node pair with only overlap neighborhoods, which equals the sum of square of structural feature values of overlap neighborhoods. If f zeta node, f zeta edge, and gphi functions has these forms, then the score is exactly same as the score from atomic order. Finally, based on this overlap neighborhood estimation process, we propose Neo-GNNs that learn usable structural features from an adjacency matrix and estimate overlap neighborhoods for link prediction. So, given an adjacency matrix A and a row feature matrix X, as we explained, Neo-GNNs compute node representation Z from an adjacency matrix, which are only based on structural information. Then, since node representation Z are based on only structural information, we compute feature-based node representation H using the conventional GNN from the given X and A. Finally, given a link, Neo-GNNs calculate both similarity scores from each representation matrix Z and H and compute the convex combination of two scores by a trainable parameter alpha. We jointly train our proposed model and individual models using three standard cross-entropy losses. We evaluate the effectiveness of our Neo-GNNs and baselines for link prediction on open graph benchmark datasets. As we mentioned, conventional GNNs show poor performance with a huge gap than that of neighborhood overlap-based heuristic method on OGB PPA and OGB collab. This implies that conventional GNNs have a difficulty in directly utilizing structural information such as degree and overlap neighbors for link prediction. On the other hand, Neo-GNNs consistently achieve state-of-the-art performance across all datasets, since Neo-GNN is able to utilize both key structural information and node features for link prediction. Further, we show that Neo-GNNs directly learn each neighborhood overlap-based heuristic method and implicitly learn the best one among three heuristic methods on OGB PPA dataset. First, we trained Neo-GNNs to fit the scores from each heuristic method on the trained set of OGB PPA. Then we measure the Spearman correlations by using lengths of test edges from each model. We analyze length correlations between Neo-GNNs and three heuristic methods based on sampled test edges. As shown in figure, Neo-GNNs show a strong correlation with each heuristic method. That is, Neo-GNNs can learn each heuristic method. Next, to show that Neo-GNNs learn the most desirable heuristic method depending on datasets, we compute Spearman correlations between lengths from trained Neo-GNNs on OGB PPA dataset and the heuristic method. As a result, correlation scores between Neo-GNNs and resource allocation, atomic order, and common neighbors are 0.96, 0.92, and 0.89, respectively. We can see that correlation scores are proportional to performances of each heuristic method, which learn the best heuristic method. If you are interested in our work and have any questions, feel free to come to the poster. Thank you.